It's great. Phelps, I'm the real professor for this course, not the fake one you had last week. So sorry about that. I had travel so scheduled I couldn't move. I'm trying a new setup this semester, and need to reclaim host on the iPad and no. Oh, all right. I'm not online properly. Let's try this. Okay. Great. So we are now okay. So we should now be streaming online. So I will be recording the videos for the course starting today. And so they will be on YouTube. I will link from them off of the web page. Hopefully you've found the web page already. And so importantly, there's a bunch of important stuff at the top, including the link to the book. This is the version of the book we're using. This book came out of class notes, dominantly the notes class. If you're looking for class, this is the book. The version, if you think this is too formal, there's something that turned into my class notes is linked off of here. All right. Oh, why is this frozen? Okay. First. Okay. All right. Other important thing is schedule track of things. Schedule. So with zero already Wednesday was practice. Started. Homework one is now out posted. Linked off of here. Okay. So we can go and see homework one. Basically starting in last week's lecture will be the material. And so it should mostly be review from a probability course. We'll be covering it with kind of a bit more flavor or data analysis how this is talked about in that space. We'll be going much faster than in those courses. The material for the homework will go through the Asian rules sort of stuff. Well. All right. So it'll be good to keep track. The videos for the homework will be posted in the video for class lecture. We posted the video lecture in the video column after class. There's a playlist if you find it. You can scan top of things. The chapters where to look for the class notes. And again, probably in the topic, I will link off there the slides I write on my iPad during class. You will also see that we will go through some code just in Colab, just you can just demystify it in case it's an issue. And that will be linked off here as well. So you can have access to all of that. And if the schedule changes, we will update stuff on this page. Right. So this will be a good place to look for it. Okay. So today we're going to be before we get started. This is the best lighting configuration found for this room. I tried this. No. Tried this. It's pretty dark. Can see this doesn't. Okay. I think this is too dark. What do you think? Yeah. This is too dark. Let me. I think you can still read it. I'll try not to write in light brown colors top of the screen. All right. Great. Okay. So then today we will be covering aspects of probability review. They'll go through material fairly quickly. Once we get through the review part, we'll slow down and kind of make sure we build up the concept. But if there's something that's unclear, or as I If I wrote something that you can't quite read, please stop me and interrupt me. One of the things you will learn in this class is the mathematical notation needed to basically read papers in machine learning and AI and sort of venues. If you want to work in this space, a lot of it is coming out very quickly. Papers using mathematical notation. So I will happily stop to explain that notation. Hopefully, I will do this already. But just in case, please stop to ask if something is not clear. All right. So the first thing we plan to cover today are density functions. And so the point of this is gives us a way to talk about continuous random variables. In some statistics courses, not the one we teach in school computing or the main one, the math they don't cover continuous probability distributions, but they're really important in data analysis. When you have an observation, model, there's some noise leading you got. Sometimes it is discrete, but sometimes it's continuous. I want to know how tall is a person, how much rain fell. And that is not really a discrete quantity. It's a continuous quantity. To understand that, I need to use these density functions. So we're going to have a random variable, which we hopefully talked about and understood from before lecture on Wednesday. Call this uppercase X. Okay. And then a density function will be again a function, and a function will be about this random variable X, and it will go from this using quantity called a sample space. Okay, this is our sample space. This is the space of all possible things that this random variable can take, all the values it can take, and it will go to that sample space, the domain of the function, the range of it will be the real value. Okay, when I write a blackboard bar with two lines on the left, that's from when mathematicians would write different letters R, they wanted to distinguish them on the blackboard. They wrote it with two lines if it was bold. And this has become a notation that's stuck for the real number, continuous space of the numbers. Okay. But in fact, it won't. All the real numbers, these have to be from zero to infinity. Okay. So they will be real values. Okay. From non-negative real values. Okay. So this will give us this will often be called a likelihood. Okay. Or a probability density function. Okay. It's not. This is a density function goes sample space for real values. The range of it. If I evaluate this at a particular point. Okay. It will be how much quantity is there. The larger the value, the more quantity. Okay. It's not yet a probability density function. For that, I need the property. For the probability density function, I need the property that for all the elements of this sample space, I'm going to integrate over them. This is an integral. Okay. If I integrate over all those values, f of x of omega d omega. So I'm integrating over all of those values. Okay. Then this has value 1. Okay. So this is me make it a probability density function. Yes. Yes. This would be like an omega or a W. This is an integral. Let me try writing this. And integral. Right. So you've taken a integral would be here. You need integrals to define these. For Yeah, the history of probability is weird. For a long time. I mean, initially they invented rules of probability, and they didn't really understand how to do continuous things. And it was through trying to understand probability, a lot of calculus and measure theory was invented. And so this is really you really need integrals for here, and they were partially invented to but exactly these so these are by default. Okay. We probably reviewed on Wednesday the rules of probability, the individual terms of kind of each entity having a probability between 0 and 1. How we can go up to infinity, not adding up to infinity, and integrals still have to be 1. Okay, so this is a little bit thing. The probability density function, once you have this for one, you often just get this as a CDF. Okay. So we think of this. Let me try and draw a picture. I love to try and illustrate stuff with pictures when it can help. Okay, I'm going to think of this is my sample space. Oh, it's off the bottom here. Okay, let me put that a little bit higher up. Figure this out for next lecture. Okay. This is my sample space, right? So I'm going to pick a value. I can pick a particular value. So omega in the sample space, I can evaluate the function. And in fact, to simplify this for a lot of examples, we will set our sample space again to be the space of real numbers here. Okay, so think of this is the probability of describing some distribution of the amount of snowfall that we will measure in the month of January. Okay, hopefully it's going to be a lot, right? And so the probability density function will be then some continuous function that's always positive, right? So I need this value to go from 0 up to potentially up to infinity, right? But this is also real values here. Okay, so it has to be greater or equal than zero. Okay. And then what's interesting is if I an integral of this, if I integrate underneath here. This integral must has to be 1. Right, so I have to be able to integrate. That's the key property for probability density function. If I know what the integral is, let's say I knew the integral was 7, I can divide all the values by 7 and make it a PDF. But we'll be treating these as probability density functions. They're continuous distributions of the amount of snowfall that we get. Okay. And so this would be measuring the amount of snowfall. All right. Okay. So the PDF is useful. It's a little bit hard to think about because I want to do things like understand and relate this back to probability. And it's weird. Right? If I say, what is the probability? What's the probability that my random variable x is equal to this value? So exactly, let's say this is 12 inches. So let's say this is 12 inches. What's the probability that I get exactly 12 inches of snow in January? This January. Yep. Zero. Yeah. It's actually zero. If I try to measure this particular quantity, it doesn't really exist. I only measure things that are these intervals in space. I need to instead say what's the probability that it falls in this range. Let's say this is 15 to 20. Right, so I can say instead, what's the probability that x is in the range 15 to 20 inches, right? And then that value corresponds with the integral in between here, right? So I can again look at the integral in this range here, right? The integral of this range, and that describes the probability. Probability is random event anywhere and fall in this range. This tells me the I can measure the probability. This is a quantity I can understand. Whereas this quantity is zero. It's kind of hard to understand. This is maybe equal to like 0.25. Right. So this is an quantity range, and but exactly a value that's zero. It's a little bit unintuitive about continuous random variables. We take that the function we have that's the integral that's mu1, and then we're into yeah, I would convert it. I would actually solve this integral and from omega in the range 15 to 20 of f of x w dw. Right, so I would solve this in half integral express. Right, and this is kind of a pain. These integrals are hard to work with. The normal distribution, which we will talk about, kind of the most famous, one of the most useful distributions here, doesn't even have a closed form for computing integral. So the continuous things are really important for the mathematics. On computers, this is like starting a table, a really fine table. It's actually discrete. It's kind of weird and annoying. This kind of dichotomy between things. But the math of using this continuous variables will allow us to think about these situations, and then computers do some really cool stuff under the hood to make it so we can actually compute with these quantities. All right. Yeah. One other thing I want to say about this is while the probability density function is useful, it's a little bit hard to work with if you're thinking about the range that you can to talk about probabilities. I like instead the cumulative density function. Okay, often called the CDF. Okay, the CDF is nice if I have an uppercase f of x. Okay. This is again a function from our same sample space to now 1. Okay, and this will in fact almost always be the real value. The sample space will always be the real value when I'm talking about the CDF. There are a couple of cases that don't come up so often that are useful, but talking about one-dimensional things where the sample space is something like snowfall, then this is thinking about real values. Okay. And the advantage of the CDF is that I can write down this f of x explicitly for a value, and this will now be the integral from w equals negative infinity to the value of the CDF. Okay, so before we add a function, let me see if this will work. Let me try one more time to see if I can get it to work. Okay. Okay, cool. All right, so now we have this function. We have and we the CDF of this function. So now we draw a nice line that is
increasing. See if I can do a little better here. It should be increasing up here and then kind of flat. Okay, and I know it goes exactly from 0 to 1 on this axis here. So this is now the f of t. Okay, and so now the cumulative function is I integrate under this curve, adding an integral, but my range starts at minus infinity. Okay, and so I'm and it goes from 0 to 1. It has to fall in this range. So if I integrate a very small value to negative infinity before 0, I can't negative snowfall. I don't think so. So then the interval will be 0. And if I say what's the probability, will be 20 inches of snowfall or less. Well, that is exactly the value right here is exactly the value t. This is now I can interpret as the probability of 20 inches or less. Okay, so now it has a nice interpretation of probability. I'll give you a value, I can ask what is probability. I don't have to talk about subsets or some intervals of these. And this, I think, if you just think in terms of cumulative functions, there's not a lot that you actually need to know about the continuity and stuff. You can always ask questions like this. The amount of quantity in a range is just the difference between two CDFs. Right? So now now I can write the probability that x is in the range 15 to 20 is equal to the CDF of 20 minus CDF of 15. Okay. Okay. I want to point out that it is very common to write PDF as a lowercase letter like usually F or G or H maybe. And the CDF, the associated CDF, is the uppercase value of that letter. And this is kind of implied that's the CDF. We'll try and be explicit when we discuss it in this class. But if you see this notation, you all of a sudden see an uppercase letter. It's the CDF of the same distribution. This is pretty common way to write. Okay. These are important things about continuous density functions. And if you can think about in terms of the CDF, there's a lot less mystery about the continuous properties that are coming up over here. We'll see a couple more joint distributions in a little bit. Yeah. Yeah, the y-axis is probability is less than that value. So the y-axis is probability. 0 to 1. Probability has to be between 0 and 1, right? A PDF or likelihood does not. It can be a value that can be arbitrarily low. Okay. What would happen if I what could happen if I didn't allow values arbitrarily large here? Let's say I talked about the snowfall and then I talked about the distribution of the snowfall here. Talk about inches. What happened if I talked about this snowfall instead of in inches in feet instead? What would happen to the y-axis? Right, the y-axis, yeah. Well, I think it's actually unless I'm making it up, I think it's going to increase by. If I went the right way. Is that right? So now if I walk one step right forward along the x-axis here. Now, before I move one inch, so I did now one step forward,
forward, and I go, okay, it's 1 foot, right? So it's small as means, but none of the probability in there change. I haven't changed anything about the information, just asking. So when I change this one, it's increased or decreased, depending on which way, right? That's a little bit confusing to think that I sometimes get those mixed up. But you can't have a limit on it because there's the information doesn't change units, and so now I need to scale the y-axis. I could, so I can't put an upper limit on these things. And that's kind of one of the reasons why. Okay, but if I go to the CDF, everything is between 0 and 1. Every question about the function returns a probability, and things work just if you had a bunch of really small of these discrete random variables. So if you're used to that, this kind of think a lot of the mystery goes away. Okay. Great. Okay. First topic cover. All right. Next one. Talk about the expected value. Okay. This is a super important quantity. Expected value. Again, we'll be talking about a random variable x. The really great thing about expected value is that the word, the technical meaning, ability in science is exactly what you would mean in English. So you probably just your first thought was the expected value is usually the right thing. And let me write this down. The definition of it, we will write an uppercase E, and I will try and use square brackets to denote the value of a random variable x. Okay. If this was a discrete random variable, then I have this is a sum. Right. I can say all of the elements of the sample space. I can sum over all the elements of the sample space. Okay. And I look at what is the value in that space, and I multiply by the probability that x equals that value. Okay. So if I have a discrete random variable, probably we'll look at an example with so if you just have a die, six-sided die, I get six different values, right? I can take sample space. If I have a die, then the sample space is 1, 2, 3, 4, 5, 6. Right? Those are the values. Each of them, the probability of each W. Each W equals X is going to be 1 over 6. Right, and then I can do relation. So the probability is going to be the sum over kind of the value 1 times 6. Instead of writing a sum here, let me write some plus signs. Okay, 1. Too powerful. Can't get it right. All right. So 1 times 1, 2 times 6, 3 times 6, plus 4 times 1, 6, plus 5 times 1, 6, plus 6 times 1. Right. That's the sum of elements of the sample space. Right. So the sample space was these guys here. That's 1, 2, 3. And in this case, an expected value. There are things I should be able to add together. Okay. They don't have to be real values. In this class, we'll deal with these elements of sample space a lot. It'll be vectors. We start using linear algebra. They could be other quantities, but I should add them up some. Okay. And then I weight them by the probability, and I can do this calculation, and this is going to be equal to 3.5. 3.5. You've probably done this example before. right?
You've actually worked out this example. Okay. All right. Shouldn't be too exciting. Again, you can also talk probability that W equals that. I can put an actual value in here that x equals 3 is going to be equal 1. 6. I can talk about
here. The expected value of something.
We could also do this with continuous random where x, if we have continuous x, then we can also talk about the expected value.
Okay.
And it's not much harder than before, except my sums become these integral. Right. So write an integral instead, but the rest of it I have to use PDF instead of the
ability. Okay, so I use PDF instead of the probability. The probability of a continuous individual values fine. Now I can write it as an integral, and this is basically the same. Okay. Again, it won't be so important that you know how to work out the integral in this class. You know conceptually what it is, and if the rubber meets the road and you really do it. In work and data analysis, sometimes you do have to calculate an integral or so, but you can use computers to do it. It's not, unless you want to double check everything. Okay, so we won't through a lot of integrals in this class. Okay. But this is the same thing. This is the continuous expected value. Okay.
Let me give you an example of a continuous function, kind of the normal distribution. Normal distribution. Let's see. F of x for this will. Let me write this with parameters. Where x is from a normal with the parameter mu and sigma. Okay. This is going to be, there's going to be some fancy stuff in front. I'll fill that in later. This is x, which is e to the power, and it's going to be x minus u quantity squared. So those could sometimes you write them as values really just be quantity squared divided by sigma squared. Let's see if I get this right. To be 1 over 2 sigma.
Okay, so this is normal distribution. Okay, this is a continuous variable. If you want to try and compute the integral, you can use algebra to do it. Well, integrate. I got this correct. It does involve square roots. That's what you need to get it integrate to 1. This is to integrate to 1. Probability distribution.
The important part is the x. Again, x to the z is equal to e to the power z.
E is the base of the natural law. 0.71. Okay. So kind of weird, but this is like a very standard distribution. And let's see, what do we? And I made a little collab to plot this. People have used Python before and used collab with Python. Have not used collab before. Okay. Collab makes it really easy. I don't have to worry about getting Kyle on your machine. It works on the web. Google product is free. I will link to this and it will compile it natively on their servers. So you don't have to worry about running on your computer. It's actually powerful. You use on collab. that aren't so bad actually for free. And as a student, you get a pro version which are actually pretty good. So if you want to do some learning for free, the Google Colab got some free access to use actually. Okay, we're not going to do anything crazy with it this semester, but just to illustrate how easy stuff can be done on here. So we're using a library called Matplotlib, which is plotting library that makes drawing pictures really easy. Helps solidify things to do. Another library that has a distribution built into it. NumPy. I guess we need that for and then math because we think take a square root. Okay, so we included that stuff. We set the mean, this mu parameter to 1, the variance parameter to 1, and we call this normal function. Okay, with and sigma. Okay. And I pass that in this way, and it plots a PDF in blue, centered around. I put the mean at 1, right? At this location here, and the blue curve is continuous distribution, and the orange curve is CDF, corresponding CDF. It has those stored in a library. Awesome for you. It's not calculating or stored in a table that it looks up actually. But it looks like it's counting in the code. Okay, and so plotting's really easy. It's a few lines, and I get this plot. I can then grab this and paste it into document. So you'll have to plot stuff for your work just to get this using this. I just want to demystify this and get you used to using it. It's very easy to get started with. Okay. This is linked up the homepage so you can see this and then use the version of it for your homework. Okay. All right. Cool. That's better than if I tried to draw myself. That's why another reason why I like to use. Okay. Expectation. What is so expectation is a really important quantity. It's a single value that summarizes a probability distribution. Often have more complicated things to capture in these formulas we'll get to throughout the semester. Capture some really quantities here, and it's described as a probability distribution, which is this weird continuous function that we can't evaluate at a single point. So we'd like to get a one value representation of it. That is the expected value. That is almost what we use everywhere. Almost everything we do in the class will be computing expected values of things. We'll be computing expected values of functions in the class. Okay, we'll be computing expected values of high-dimensional vectors of all sorts of things. This will be kind of most of what we're doing is kind of a representative example of a distribution. You want one number or one entry object to represent it. Expected value is almost always your choice. Not necessarily because it is the most stable thing. Usually because it's easiest to compute. Okay. So computation plays a big role in choosing what we choose to do, and the value of the computation is often very easy. Okay. Yeah. This is coefficient. This is once I specify I think I just set this as one or two example. This is constant. The only variable here, lowercase x, lowercase x is up here. So this is the shape of the curve. This part I described the curve. That's that L function, right? And then this tells me, well, I need to scale it so it integrates to 1. And that's why mathematicians probably worked out this integral model and said put this in front of the integration. Yeah. So this you can almost not worry about. And we will play with this function over the next few lectures, and I will show you mathematically a bunch of cases where you can why you ignore the front. For now, it's here. Okay. So you can't always ignore it. Okay, but in a lot of cases you'll be able to, and I will explain exactly why that's the case. Okay. Great.
Okay. Very good. Okay.
What is
one of the reasons expectation is so nice is it has this property, linearity of expectation. This is aside from the
this is the most important property about expectation. Okay.
So you should know what the definition is,
right? These two black things for discrete US. Okay. Know
those definitions for your quiz and homework and everything, and just in life, it's useful to know.
The linearity of expectation. This is kind of the next most important thing to know.
Okay. So now I'm going to talk about two random variables. Okay.
Instead of writing out, you haven't noticed, instead of writing out random variables, you also write RV in uppercase RV,
shorthand. Okay. Now I've got two of them, X and Y, uppercase Y.
Okay. Yep.
And I want to go off. Let's say I want to compute. Right. So we're back to computation again.
Why is this expectation so nice? I want to compute expectation of X plus Y. Okay, and if you're a scientist or probably so you understand the order of operation. I want to do X is first it's rapid function expectation, right? So I want to add them and then expected value.
But it turns out I can do this instead. I can write the X value of X plus the expected value of Y.
I can decompose it. 3 can be the expected value of X. 3 can be the expected value of Y. I can add them up, and I get this plot. Right. This is super useful. It'll be super useful. Computational reasons, mathematically throughout this. Allows me to decompose complicated function into much simpler pieces. Okay. And that's not all.
Let's also say I have a fixed scalar value. Okay. Do you know what I
mean when I say a scalar value? What does it mean when I say scalar? When I just say value? It's going to be a multiple. Yeah, scalar means it's not a vector. It's just one
value. It's going to be, let's say it's a real value here.
Okay. We'll talk about vector values later. Vector values will be more complicated in here, but let's say it's scalar value. This will be kind of a coefficient.
So now I want to write alpha X. So I want to
multiply my variable is function. This weird way that's work. And I have a sort of quantity, a coefficient in front. I want to play here.
What's that equal? I can do alpha times the expected value of X.
So now I can pre-compute or have the expected value of X and just allow this constant coefficient. Again, this is super nice and useful. Yeah. In real life, great question. Well, there's one example we talked about already. We were looking at snowfall in inches. What if I want to convert this into feet? Or I have a friend in Canada and I want to convert it into meters, right? That is a constant value. That's a scalar function versus units of these quantities. And I can compute the value in feet or inches. I already have that, and then I just multiply quantity. You don't need to do all my calculations. Right. But also do things like alpha can be minus one or something like that. You can take the negative of it, and that just takes the negative of the expected value. Right. So all sorts of cool stuff. We'll see more and more powerful approaches for using this linearity of expectation. Okay. What is not true? But let's say I have the expected value of X multiplied by Y.
see if I can write a Y appropriately. Okay, and this is a multiply, right? X multiplied by Y. It'd be nice to do E of X times expected value of Y, but this is not true. Okay? This does not work. Okay.
So I cannot decompose the product into random variables. If it's a fixed quantity, like a scalar, like conversion between units, okay, I can pull that. But if it's two different random variables, I can't do this.
Okay, so don't overgeneralize here. You can do
addition, you can do multiplying by constant, but not multiplying of random variables. Yes. If they are independent, I can do this, but non-general.
Yeah. If I have independence, I can do this, but not in general here. And we will see the importance of that as well. That's see that in a week or two why that's so important. Okay. Okay. Let's go through a question.
Bobby multiply them together. Right. Okay. So let's say that I'm going to look at the distribution of snow, X, and I'm going to look at distribution of how much money Snowbird will make this year. Okay. And I think it should depend on the snow some. Right. So it's not independent of the snow. So I don't have independence here, but I think so I just say not the amount of money will make per snow. Okay, maybe that's so let's say let me give another don't have one prepared here. Let's say I can. Okay, so let's give you a oil. Okay, let's say how many oil barrels of oil I can pump and the price of oil. Okay, so how much money I will the revenue I will earn depend on how many barrels of oil I pump plus the amount I can sell them. They're both random variables, and it's the product of each. Okay, but I can't just the probability of barrels and this distribution of the price. I do want the expected value of profit, but I can't individually and take the product because they're not dependent. Actually, the price will go down if I more barrels. So this is I need to look at joint distribution. Yes. Okay. We'll get to this in 15 minutes. Yeah. We're going through the whole semester very quick. Great. Good. All right. For linear expectation, I want to kind of go through a silly kind of example. Have to do with the height from the textbook, and I want to kind of again try and make you feel kind of more comfortable with mixing discrete and continuous. So random variables. Okay. So I've got the kind of the true height of a bass player. Okay. And we'll say the quantity H, and that means they're standing with their bare feet on the floor. Okay. And then I want to have the height of the shoes.
Okay, so it used to be when basketball players went to the combine to get measured before the NBA draft, they would go in shoes, and the heights were all over the place because they wouldn't be uniform, and they have stopped doing this, in fact, because it was too complicated. We're going to go through it anyways. The reason is that you could do a bunch of different shoes, and so the two random variable, let's say it could be in inches, and the number of, or let's say this is in centimeters. The inches of the shoes depend on if what sort of that you actually played in, or how tall you want it to be. 1 centimeter maybe was 0.1 probability. 2 centimeters, there were 4 brands of shoes that people wore to simplify things. Okay, and there are, let's say there were only 4 different types of shoes people wore.
Right? They wore only 4 different types of shoes. They each have a probability. So this is weak probability. Now, because there are only 4 different types of shoes. One shoe, like these Hoka or something, and they have 4 big boots, like 4 inches, 4 centimeters height. Maybe a third of the players this, and half of them more 3 centimeters, and a few more like 1 centimeter. Maybe they had more kind of control. They were a faster player. Okay, so I have a discrete probability, and then I have a distribution on the height, on the actual variable, and maybe this was normal distribution, which was I wrote this was in meters was kind of a good average height in meters, 1.755. That's close to my head. That's the average height of a male. That's looks about right for that. Okay. And I have standard deviation 1 meters. Okay. And so now I can write the expected value of the height variable with the normal distribution. I know that this is going to be exactly 1.755 meters. I know the expected value happens exactly this way. One of the reasons. Yeah. This is n for normal distribution. This is kind of a script n for distinguish that H is described by a normal random variable. Continuous random variable, we use one of a small number of ones we have studied and know all this out. So we have lookup tables in this song. The normal is the one I plot of. A distribution. I don't know let's say this gas the height of the person. There's measurement here in it, or it's random person through, and let's say this is the distribution. Okay, so there's some representation of this distribution, and the mix with the sort of shoes that you wear. He's not a basketball player, it's a random person. Okay, so I'm going to draw a random person, and they're the space of people, maybe there's a discrete number of people, but generating new people. I guess. And so this is kind of an average height of a person I haven't not measured before. Okay. And so it's expected there. Okay, so now I want to compute the expected value of the person in shoes, right? If they're wearing their shoes, you go to the doctor. You are kind of an instance of this distribution, but in shoes, I need right. Well, it's the true height. Okay. Plus the shoe height. This is your height when you're walking around in the world. But the shoe height, the shoe height measured in centimeters instead of meters. So I need to divide this by 100 the height in meters, which is easier to kind of think about quantity. So I divide that by 100. And so this calculation ends up being the expected value of the height plus 1 over 100, the expected value of the shoes.
Okay. So now I can calculate that this is 1.7755 meters plus
Expected value.
I calculate this, I get this is 3 centimeters. You can work it out. Okay. So that is plus. Okay. 1 over 100 times 3 centimeters. And this was equal to 1.785 meters. Okay. So this is my answer.
Okay. So I can use the expected value. I can combine together random variable, a discrete random variable, unit, and I can compose them, and I compute all the quantities individually with ways that should be familiar to you, but it makes it very easy to combine stuff together with sorts of different properties of space. Okay, so it's kind of a silly example, but I think it illustrates the power of linearity of expectation. Okay, and hopefully helps demystify these continuous random variables more as well. Okay. So the next thing, important quantity we've already been talking about a bit is the variance. Okay, and this will again having to do with the random variable x. And now the variance of x. I write it and then bracket again around it. Okay. And so this I read it that way because the variance is exactly an expected value of x minus expected value of x, this quantity squared. Okay. Hopefully again, this should be a review. You've probably seen this before. A few things to point out. This term here is a constant. Okay. The expected value of x, if I given the random variable x, this is a constant in the black formula there. That inside expected value. So when I compute this, I basically compute the expected value first, and then I get in the constant inside this formula, and then it's expected value, which I know the formula for. It's either a sum or discrete random variable, or integral for continuous for continuous random variables. Okay. Okay, and I can rewrite this. It turns out it's equal to the quantity expected value of x squared minus the expected value of x quantity squared. Okay, and this you stare at this, you're like, is that always zero? Right. If I can do some algebra to actually get from one expression to the other. But why is this always zero? What do we see here?
Expected value of x is totally different. Square.
Great. Yeah. So I want to do linearity of expectation, and then pull this side, but I can't do this. Is multiplying a random variable by itself. Okay, when I multiply it by itself, I can't factor that out of the expected value, and this is pull that out of the value. I can't do that. So this is not. This is not always, generically, this is not zero. And this is a good formula to remember not to do this sound, right? Remember, don't do this. But you cannot generically do that term there, multiplying them, and this otherwise this would always be zero, and it would be very useful. Okay. And what? How do I think about the standard deviation, the variance? Okay. The variance I want to think about real value random variable, and I want to think about a mean, right? And I'm going to think about
a normal distribution. Right, so now I have bell, this bell shape, normal distribution. That's why I plotted it, because it's kind of hard to draw, but okay, let's pretend that's
pretty good. Kind of like a normal distribution here. The variance is kind of
makes a lot of sense. This is for f of x, where x from this normal distribution with mean mu and standard deviation or variance. I guess we use with standard deviation sigma.
Okay, what is the variance? Telling us the expected squared distance from the mean. If this is the mean, if I say that average is zero, it's something with no bias, zero, but we talk average person, 17555 meters. Right, so that coverage here. The normal distribution, how much noise it has because off of here. Okay. And question? Right. So that's why I want to get to this figure really good illustration of this.
I wanted to draw about this picture here.
This is sigma. Okay, this is how you draw normal distribution. And you go out halfway up, and then you look at how far over you get to the edge. Good ballpark. That is sigma
is the square root of the variance of x, which is called the standard deviation. Okay.
So I haven't drawn variance of x a lot, but I've drawn sigma instead, standard deviation. Why? Where would I draw the variance? Can I draw the variance on that? How would I do that? This is kind of the easy draw. But what is? How would I draw the variance? It's hard, right? It's not clear how to draw it. Right. That's because there's a good reason for that. The variance is a squared quantity, right? It's expected, it's square. What are the unit variance? I'm bringing the unit of the variable meters. Squared meters, right? What's the unit of standard deviation? It's meters, right? Okay, that's great. I can draw this height in meters, draw something in meters on here. Makes sense. I can't draw something in squared meters. Maybe some like three blue, red, brown, or what's it called? Three blue, one brown. Probably draw some cool thing with boxes and stuff that I illustrated. Okay. I bet this videos are better than my lecture snippets. Okay, but I'll tell you, you can't plot on the picture. You can draw the standard, but not the variance. Okay, because the units don't match, and that's why standard deviation is so common to use instead. Okay. But the standard deviation is an ugly square root on top of it. No one wants to compute square roots. Okay. I don't want to think about square roots. I don't want to compute them. They're kind of a mess. But I need to do it to get to the right units. Okay. Variance is nice quantity that's easy to kind of calculate and work with, and it's kind of the right measure of how spread out the distance is. Right. So if I have a normal distribution,
I can completely describe it by these two parameters, the mean and the standard deviation.
That completely describes the normal distribution. Those are all two values that describe this whole continuous kind of beautiful. I butchered a little drawing, draw the Python. Okay, so I really need to describe the mean and how spread out it is. We'll use two values with this distribution. These are the two values you use. Okay. The association is interpretable. So you write units. Variance is very hard to interpret. Some square quantity. If I wrote down the square quantity for this case, the players, the square quantity of 0.11 squared. I don't know how to think about it. That's very hard to conceptualize, but 0.1 meters squared, I kind of know, okay, well, the mean is here, and then about 0.1 meter, right? Most of the mass in there. Okay, most distributions will have usually these parameters, equal ones, center parameter, often the expected value, but not always, and then a kind of hill parameter spread out as it. Okay, and we can go list of them, but we're not going to do this normal distribution. This is the one. This is the one we like in class and in most of it. We'll talk about a couple of other things, but the normal distribution one you should know. This formula, you will hopefully eventually memorize this formula. It's not. It looks like it's a mess, but you should eventually memorize this formula. We'll work with it enough and understand why you can thrive all the algorithms. Okay. What happened is people up with all these really algorithms, data analysis, and then later like, why did this work so well? And how we came back to based on if we assumed we had normal noise, this was the right thing to do. And so we'll kind of go in the other order. In the class we will derive a bunch of quantities with the normal distribution and very simple quantities, and then we'll go and them the rest. Okay. Yeah. No. All right. You're asking all the really questions here. What is noise here? Not really. It is. I'm trying to come up with an answer that's a minute, and I'm kind of it's complicated. What is it? What does noise mean? So we will discuss this. This is a fantastic question. Okay. And we'll be better off asking this again in a few lectures. Okay. We'll talk about how to model various types of noise and think about it. And then you can debate afterwards if that makes sense. This is. I would say this is not a quantity. Okay. This class is going to go through and give you down the middle mathematics, try and give you the best, simplest, clearest explanation why we do most in data analysis. This is an evolving field, and some people don't believe certain types of noise exist. We're going to model this because it will the explanation of how you get the basic and drive the basic simple and clear. The answer is not. Okay. So but think of you try and measure height with a measure and you're off by a little. That little bit drop, they were wiggling a little bit, or your measure was not quite on the floor. That's noise. Okay. And we're gonna modeling that now with probably distributions. And in particular, the normal distribution here is everyone's favorite model. Okay, and we'll stick with that. There are a whole field of statistics, more or less as a given. And I am saying people who are debating that premise actively in right now. So let's okay. Okay. That's your probably a little over 1 minute answer, but that's a great question. Let's keep asking these first. Okay. Let's see now. Okay, I have 10 minutes to tell you about going random
variables. And then we get into much more. We'll start to slow down. Next, starting with next lecture, we'll get back into Bayes rule. You've probably seen Bayes rule a bit before. We'll start to really use it first. So to talk about Bayes rule, we again are in the situation or joint random variables when we have x and y. Okay, and these are both random variables, and they're not necessarily independent of each other. Okay. And there are a couple things we can talk about. One is the covariance. Okay. The covariance of x and y. And this is a version of the variance, but it's a very other. So again, it can be written as an expected value of x minus expected value of y of x times y minus the expected value of y. Okay, so what I'm doing is what x gets larger with respect to its means. Like think of subtracting off the means from everything, so they're centered zero. And then what happens now if something is larger than average. When x is larger from average, y usually larger from average. X is less than average and negative. Y also usually larger than average negative. When I multiply negative values, they become positive again. So if they both positive or negative together often, that gives me a positive quantity. If they're both one's positive, the negative, they get negative quantity. So the larger the positive is on average, this is an expected value, and the covariance is positive. They vary together. If it's a negative value, when one increase, the other tends to decrease. Okay, so this is kind of a simple one value snapshot of a pair of random variables. Okay. But we want to talk about more the PDFs as well. So we can also talk about the PDF, the joint PDF. And now I would write as f of x and y with little x and little y is evaluate them. Right. So this is okay. So this is a function. This is the likelihood PDF for the likelihood of x and y. And so this is kind of like it's kind of like not exact, but the probability that equals x and y. Okay, so this is not exactly. So if there was a discrete random variable, okay, but if it's a continuous random variable, exactly the probability, I want to say probably that they're both true. It's the likelihood that they're both x, big X is equal to x, and big Y, the random variable is equal to little y. Yeah. Just ignore that. Me. I was trying to figure out what to write to tell you. This is not write this down as true, but this is what we're thinking about. Right. I want both of these quantities, both of these things realized at the same time. I need them both to happen. Okay. And to write this down formally, I need something like this is actually equal to. Oh, I'm gonna. What's true? The probability function is. So I can't. I mean, I actually evaluate it. It's actually equal to zero at any given look if continuous. Okay. Well, the property I have is that if I integrate over the domain, let me write this a little bit clearly. If I integrate for the samples of x and I integrate the sample space of y of f of x, y at these values dx dy if it's probability distribution function, then this integral have to be 1. So now I have two-dimensional that integrates. Okay, it's a little to draw a picture of this, right? But think I'm drawing something on the table here. It's got some bumps. Imagine, and if I integrate double integral, that integrates to 1. Okay. I'm glad you like my dance. Okay. So we need to be able to do this. Okay. So you probably also learned, hopefully learned or reviewed last Wednesday about marginal distributions for discrete random variables. So we had this thing of a table. The marginal distribution is I marginalize something out. Right. So then what I want to do, and I want to write. So the marginal distribution. Okay. That will be f of x marginalized out y. Okay. So this is going to be equal to my gosh. My class notes. This will be. Okay. Yeah. So this will be often written as x given. So this is. Sorry, this is the conditional distribution. Okay. So the marginal distribution. So I have the joint random variable, but I want to write down the marginal distribution. This will be equal to the integral from y equals negative 1, negative infinity to infinity of x, y of x. That's some value x. dy. Right. Right. So this is the marginal distribution space here. Right. I've got x and my y. This is sample space of y. And you can think of having some function over here that I have to integrate over this function. That's hard to draw. And what I want to do is integrate out the y direction and just get a single function here. So then I want to have the same sample space x, and I want to get integral here. This is now f of x. So I've integrated out the y. Everything for a particular point. This is a lowercase y. I looked at the line here that goes that point lowercase x, and I integrated a long line. I said, what is the integral once I fix this value x? Okay, and that's what it's doing. Gives me the. So I think of going from the table, but now I have a two-dimensional picture. I'm marginalizing out the y variable down to a one-dimensional kind of picture here. Okay. And then the other thing is the conditional distribution. Okay, you can define this is f of x given y. So we'll often write this as x little x given little y. This will now be written as this would be the joint. Yeah. So this is easier to write down. This is f of y of x and y together divided by the marginal. Make sure I get this right. The marginal distribution of y. Okay, so remember the additional distribution for discrete random variables. You looked at probability of both true divided by y. Right. So this was instead. Now I'm thinking. Let's for this case we're going to fix a quantity y And I'm going to say, let's say this is true.
Condition of I being true. And now I can one-dimensional condition. The slight or the kind of the ridge line of that red function, assuming y is true. So I need to divide out by the integral of y being true here. Okay, so imagine you're walking in the mountains in Utah, and you decide, I'm going to exactly in a straight line that is y being true. And I'm on the straight line. What's the probability of how far I am, or the probability I'm more likely the higher the elevation? That's what the conditional distribution X and Y Sternberg. Okay. We have reviewed a large amount of probability class in one lecture. We're going to start to slow down, starting the Wednesday's lecture and start reviewing Bayes' theorem and how important this is, and then we'll using this to do a little bit data analysis and derive most of the most common things from this one